The if decision statement and the variations on it are very powerful statements. There are many programs that cannot be written without a decision statement. They allow us to write code that executes different code for different input values. They also make code more complex, as unlike previous sequential programs we've been writing, we can't look at a program and know exactly which statements will execute. As we've discussed in an earlier video, this also makes it more complex to test your code, as you need to make certain you test each possible ordering of statements that might execute. One of the keys to being a successful programmer is to learn different techniques for solving problems, and when you encounter a new problem, recognize which techniques that you've learned in the past could apply to the new problem. As with most things in life, these past experiences make you better able to handle new situations that are similar. Now that we know the Python decision statements, the section of the book this video covers uses a number of different techniques to find the maximum value of a group of numbers. Some are tricky to get right, and some do not extend well as the number of values we are trying to find the maximum of increases. One is similar to the accumulator pattern and can easily be extended as the number of values increases. We'll start with this example showing a function to find the maximum of two values. We can use the if statement to determine which value is larger and return that value. It should be fairly easy to see that it will work correctly, although one thing we should worry about is what happens if both values are the same. In this case, it would return x2. Since the values are the same, it does not matter which one we return. That means we can use either a greater than or equal comparison for the condition. Also note that we could write it without the else clause and just return x2. If x1 is larger, the first return statement returns x1 and exits the function, so it does not execute the code after it. If the condition is false, then it returns x2, which is what we want. Even though the code is shorter this way, most programmers prefer the original version. It makes it more clear we are returning one of two values depending on the result of the condition expression. Also note that I've added these comment lines to separate each function. Many programmers do this, although it is becoming less necessary as modern development environments make it easy to find functions by name and support code folding. We can click here to collapse and hide the function body, and click again to unfold it. This version attempts to extend the max function to handle 3 parameters. The first version is not correct. It also demonstrates a syntax that works in Python, but not in most other programming languages. Python allows you to write consecutive comparison operators. In this first case, it checks if x1 is greater than or equal to x2, and if it is, then checks if x2 is greater than or equal to x3. So for this first condition to be true, x1 must be at least as large as x2, and x2 must be at least as large as x3. Most programming languages write this using the word and, or symbols for and. Python also supports the keyword and we could write the condition as the comment shows. We'll learn about the and keyword and other Boolean operators in a later video. If both those conditions are true, x1 is the maximum value, so we can return x1. The elif handles the case where x2 is greater than or equal to x1, and x1 is greater than or equal to x3, and returns x2 in that case. If neither of those is true, it returns x3. This might seem correct, as any one of the 3 values could be the maximum, and we've returned x1 when it must be the largest, and returned x2 when it must be the largest, and then returned x3 otherwise. The problem is we haven't handled all the cases. The second version fixes it by handling the other cases. One case the first version didn't handle is when x1 is larger than x2, but x3 is not smaller than x2. Or in other words, x3 is between the other 2 values. You can see in the incorrect version, when we returned x1, x2 is between the other 2 values. There's also another case when x2 is the maximum of the 3 values. Our original incorrect version returns that x3 is the largest in these cases, which is not correct. This should convince you that testing your code is important, and it can be difficult to be certain you've tested all the possible cases. We'll run it and see the first example works when the values are in descending order, but doesn't work when the last parameter is the middle value. The fixed version works for this case also. If we want to be certain the new version works correctly, we should test it with values that check each case and convince ourselves we handled every possible option. There are 6 different ways you can arrange 3 values, and we only have 5 options. But the else case effectively handles 2 cases. When x3 is the largest, either x1 or x2 could be the second largest. But we know if none of the previous 4 cases were true, then x3 must be the maximum. Extending this approach to find the maximum of 4 numbers would be a lot more work, as there are 24 possible ways to arrange 4 numbers. Since it isn't very feasible, we'll keep looking for different approaches to solve the problem. This version is known as a decision tree. We first check whether x1 or x2 is larger. If x1 is the larger of those two, then we just need to check which is the larger of x1 and x3. We have the mirror image case for when x2 is the larger of x1 and x2. In that case, we just need to check whether x2 or x3 is larger. Now let's think about how to handle this for 4 numbers. We can see that we first check whether x1 or x2 is larger. If x1 is larger, now we need to find the larger of x1, x3, and x4. This is the same problem we just solved with the previous version, so we need to write the same code using those variables. Or we could call the max of 3 function with x1, x3, and x4 as the parameters. I've written it out so you can see the amount of work. When x2 is the larger of it and x1, we need to find the maximum of x2, x3, and x4. As you should be able to tell, we'll need to double the number of if statements every time we add an extra value, so this won't work very well for a large number of values either. Now we'll look at this version from the book that should remind you of the accumulator pattern. We're essentially building up which value is the maximum by checking one number at a time. We'll write this version for 4 values to see that it is only one extra step for 3 numbers versus 4 numbers. We start by setting the current maximum to x1. If we only have one number, it clearly is the maximum of that one number by itself. Next we check whether x2 is larger. If it is, we update max value. So by the time we complete the first if statement, we know that max value holds the maximum of x1 and x2. Next we can check whether x3 is greater than max value. If it is, we update max value. Since max value is the larger of x1 and x2, after this if statement, max value will now hold the larger of x1, x2, and x3. And finally, for the 4th number, we repeat the process. If we had more numbers, we would just need to add one more if statement for each value. This version scales much better than the other versions. Determining the most efficient way to solve a problem is a common theme in advanced computer science courses. The book has a version that shows we can use a loop to handle as many numbers as we want. The program first asks the user to indicate how many values we will be handling, so we can write a for loop. We could also enter the values as a string, split it on the separator character, and iterate over that list of strings, converting each one to a number. The key point to realize here is we need to set max value to the first value. Otherwise, the comparison statement inside the loop would not have an initial value for max value the first time through the loop. Now the loop can execute one fewer times than the number of values, and have us input each value and update max value, just as our previous version showed. This code will work for any number of values. The final variation shows that Python has a built-in function named max that takes an arbitrary number of parameters and returns the maximum of those values. It works the way the previous version did, by updating a variable containing the largest value found so far. The previous versions gave us some different ways of solving a problem. You can think about applying those different techniques to new problems you encounter. This version shows that it is important to know what is built into the language you are using, so you can save yourself a lot of work. Not only is it less code to write, but we can also be very confident it works correctly since it's part of the language.